Hey there, pre-calc students. This is Miss Adams from Flamingo Math. Let's finish up our lesson today on parametric functions, modeling planar motion. Starting in example 4, we want to think about Debbie hits a golf ball with an iron, and that can be used for short distances while you're approaching the green. The parametric equations that describe the position of the ball as a function of time are given right here. We want to find the real zeros of the function where x of t equals 0. So x of t is 40 square roots of 3 times t. So where is 40 times the square root of 3t equal to 0? That would happen when t is 0. That tells us x of t equals 0 would correspond to the y-intercept. In other words, that would be the initial horizontal position of the golf ball. We want to find the real zeros where y of t is 0 and explain the meaning in the context to this scenario and support your answer algebraically. Taking our y value, negative 16t squared plus 40t, solving that for 0, we can factor out a t and a 4. We can make it negative 4t, so 4t minus 10. That would happen at t equals 0. That would also happen when 4t minus 10 is 0. 10 divided by 4, that's 2.5, so at 2.5. So when y of t equals 0, that corresponds to the x-intercept. And when t equals 0 indicates the time before the ball is hit. But when t is 2.5 seconds, then that means the ball hits the ground at its maximum horizontal distance. For part C, explain how to determine the maximum extrema for the equation of x of t, and what is the meaning of this maximum in context to the scenario, and support our answer algebraically. So our maximum horizontal distance occurs when t is 2.5. And if we looked at the x of 2.5, that's 40 times the square root of 3 times 2.5. Using our calculator, that's roughly 173.205 feet. So the maximum distance the golf ball travels in the air is about 173.2 feet vertically. So that we can write that in a sentence to explain the context, the meaning and context, the maximum distance the golf ball travels in the air is about 173.2 feet. 173.2. Okay, in part D, we want to explain how to determine the maximum extrema for the equation of y of t. Well, we know that the maximum height is going to be the vertex, and the vertex is opposite b divided by 2 times a, since the path is quadratic or parabolic. Path is quadratic. So solving for t, that's at 5/4. That tells me the y of 5/4, substituting, is 25 feet. What does that mean? That means the ball is going to reach a maximum height of 25 feet. So the ball traveled horizontally 173.2, and the ball traveled vertically 25 feet. Let's go on to example 5 and see what that holds for us. Here, Sammy hits a ball when it is 4 feet above the ground. We have an initial velocity of 120 feet per second. The ball leaves the bat at a 30-degree angle, which is pi over 6 radian, and the horizontal and heads towards a 30-foot tall fence that's 350 feet from home plate. So we're talking about baseball here. I think I like baseball. Let's think about this. So we've got a y-axis and an x-axis, and out here at 350 feet there's a wall. So we don't know whether the ball is going to hit the wall or not, but we've got, let's see, 4 feet above the ground, so we're going to go up like this, and we want to know, does the ball clear that fence? So this is the wall or the fence. Our x-coordinate is 120, because that's the velocity, and x is cosine of pi over 6, so 120 cosine pi over 6t. And then y of t is going to be in feet, so our gravitational constant is 32 feet per second per second. Half of that is negative 16, initial velocity, and then the sine of pi over 6t plus 4. So will the ball hit the wall? Does the ball clear the fence? And using the trace feature, I know that the ball hits the wall. So we said by using trace, and if you do this with me, at about t equals 3.37 seconds, the ball is at 24.9 feet in the air. And we've got a 30-foot fence. So if I labeled my x-axis here, we're at 30 feet. We started at 4 feet high. And part C, if so, by how much does it clear the fence? If not, could the ball be caught? So what I did was I set my window, get something here. I had my window set from 0, 10, and I was going up in steps of 0.13. I set my x-axis from 0 to 400, and I set my y-axis from 0 to 100. So if you want to follow along on your calculator, that's how I determined I would hit the ball. So tracing that step, I got 24.9 feet high. So the ball is not at a reasonable height for a player to jump up and catch the ball in flight without hitting the wall himself. And then lastly, example 6, Denise hits golf balls off the tee with an initial velocity of 80 feet per second with her driver. We want to write a general formula for x of t that will calculate how far down the fairway the ball hits the ground if it comes off the club at a pi over 6 angle with the horizontal. So I have my 2 equations written first here as step 1, and then can we write a general formula that will calculate how far down the fairway the ball hits the ground if it comes off the club, making that pi over 6 angle with the horizontal. So our general formula, what I did was I took the y equation, I factored out a t, and found that t was 0, which would be before the ball's hit, or t is 5 sine theta. So if we go back up to our x and we put t value is 5 sine theta, then our general formula could be written as x of theta, because now we're switching over to theta and not time, is 80 cosine of theta times 5 sine of theta as our replacement for t. And if we put 400 x of theta is 80 times 5, that's 400 cosine of theta times sine of theta, then I can use that in step 4 when my theta is pi over 6. We have 400 cosine pi over 6 times the sine of pi over 6, and that calculates to be 100 square root of 3, and that is about 173.205 feet. Oh, we had one more example. And then example 7. In a game of lawn darts, Kevin throws a dart upward from a height of 3 feet with an initial velocity of 35 feet per second. The angle of inclination is 4 pi over 15, which is roughly 48 degrees. And we want to consider the position of the dart in any time t, neglecting any air resistance. Can we find the parametric equations that model the scenario? X of t is the initial velocity, 35, cosine of 4 pi over 15, or 48 degrees, depending on what you're used to in class. And then y of t in feet would be negative 16t squared plus 35 sine of 4 pi over 15 t plus 3. Then if we graph that graph in our calculator, make a little sketch here. My x-axis is time, and my y-axis, y of t. We get a picture that's parabolic, starting out here at 3 feet above, and it's going to go over here. So I know at t equals 0 is where we have a y value of 3. But over here, this t is about 1.73377 seconds. So if I evaluate the x of 0, you get 0, but the x of 1.73377 is about 40.604. So the possible values of x have to range between 0 excuse me, and 40.604. So let's erase that so we know our x values go anywhere from the x of 0 to the x of 40.60414. And when will the lawn dart hit the ground? Well, we just figured that out. So we really did C before we did B. The y of t is 0 at t is about 1.73377 seconds. So we can round that 1.734 seconds. And then for part D, at what time, t, will the dart reach its maximum height? Again, I'm going back to the equation t equals opposite b over 2a to find the x or the t coordinate for our vertex, and that's going to be negative 35 sine 4 pi over 15 divided by negative 32, and that's going to be 0.8128. So the time is about 0.813 seconds when it reaches its maximum height. And then for part E, to find the maximum height of the dart, we would want to find Maximum height would be the y of 0.8128, substituting negative 16, 0.8128 squared, plus 35 sine 4 pi over 15 times 0.8128 plus 3. Carefully on our calculator, the maximum height of the dart is about 13.5705 feet. And that finishes the lesson on parametric planar motion for section 2. See you around for section 3.